Okay, so let's talk about near the end circle definitions, theorems. And just so I give my voice a little bit of break, we'll kind of go around the room. Uh, can you read the box in the upper left corner? Like there's those four definitions in bold.
Circle. The set of points in a plane equidistant from a given point, the center of the circle. Radius. A segment from the center of the circle to point on the circle. The distance from the center to a point on the circle. Circumference. Distance around the edge of the circle. Congruent circle. Two circles with the same radius.
So every single segment, thank you, Cam, appreciate it. Every single segment I'm drawing, what's true about each of those purple segments? How are they all related? They're all equal. Because what am I doing? I'm starting from a center point and going out to the circle. The definition of a circle, they call it the Euclidean definition. It's kind of a funny word. It's named after, I think, a Greek mathematician like thousands of years ago. The Euclidean definition is this right here. It's a set of all points of equal distance to a fixed point. You have a fixed point, which is the center. At any point that is equal distance, you can connect all those dots. What do you get? Circle. That's it. Now, congruent circles are obviously circles around the same radius. Circumference is this all the way around from the 2 pi r's, and radius is that distance, right? So those are all, I think, very basic definitions. Should be very comfortable with that. Okay, let's move on to the top right corner. Connor, can you read the all the information in the top right corner? Oh, you're done. Good.
The right.
Yeah, top right. About diameter. Welcome.
Diameter, a segment that goes through the center of the circle with both endpoints on the edge of the circle. Chord, a line segment that goes from one point to another on the circle circumference. DI is the diameter. CH is a chord. DO and OI are both gray.
Thank you. Perfect. Thanks so much. So chord. I'm not sure if this helps, but you have a chord in a guitar, perhaps, because the guitar connects one end to the other end. I'm not sure if that helps. I don't know, but that's what a chord is. A chord connects one end to another end. Now, somehow the chord could be a diameter. The diameter is a chord. Actually, the diameter is the longest chord, right? I can't think of a chord any bigger than that. But CH is a chord, just a smaller chord, you know. That's all it is. Just connects 2 points on the circle. That's it. That's all chord ever is. Again, sometimes the chord could be the diameter, right? So, of course, DO and OI are radii, and you don't say radius is, you know, it's weird. Radii is a plural of it. So, just something to keep in mind. Okay, so just so you know, that's what a chord is. That's a chord. And you might forget these definitions after today, but we're going to keep reminding you of it often over the next 2 or 3 weeks. William, can you read a part about tangent?
A line that intersects a circle at only one point. The radius at the point of tangency is perpendicular to the tangent. Tangent segments theorem. Tangent segments to a circle from the same point.
Oh, no. Just everything in that box. Sorry. IG is a tangent. Or is that TG? Yeah.
The point of tangency.
Right.
A line that intersects a circle at 2 points. ST is a secant.
Perfect. Thank you so much. All right. So let's talk about these terms. These are probably new terms for you guys. Like if someone says you're going off on a tangent, what is that?
It means you're definitely.
You're asking about some nonsense or something else that's not related to the topic. If I start talking about the NBA playoffs or the Giants with the Marlins, or I'm going off that thing, right? So I don't know if it helps, but like you see how this line just grazes the circle? It does touch it. This green line touches that point T, but it's sort of just grazing it and just it kind of just goes off and does its own thing. So that's called a tangent. Always, this is perpendicular to the radius. So if I draw a tangent line, meaning it touches just one place, that's it. Not twice, but one time. The radius will always be perpendicular. There you go. Okay, cool. So that's all it means. So TG is a tangent, and T is a point of tangency. And then OT, of course, is the radius, so it's perpendicular. They'll always be perpendicular, you know. Which means we're gonna do a lot of problems with stuff. We're gonna do a lot of Pythagorean theorem. It's gonna be happening, even some trig maybe, you want to throw some there. Secant, I know it's kind of funny. It might be hard to remember, but secant is not a chord, but it's a line. A chord is a segment. So it's like a chord, but it just extends in both directions. So it intersects the line, sort of 2 points. It goes up and down forever. So that's a tangent. Zoe, can you read the part about tangent secant theorem?
Two circle for the same point outside the circle are two.
Yeah, so tangent segments, that's secants. Tangent segments. Yeah, so if you have two tangent lines, so that's a tangent line, and that's a tangent line. Here's what's going to happen. And we'll investigate this in more detail later on. Let's do different colors. Do green. If you think about it, and this ties back triangle congruences. Don't worry, I'm not going to do proofs. Actually, there's no proofs in this unit.
Yeah.
Right. It's all computations. But think about what's happening here. Are both of these right triangles? They are. And actually, let me put an extra letter here. Let's call this A. Is AJ the same length as AF? So from the center to J, the center to F, are those the same? They are. What do they both represent? Radius, perfect. Good. And you have right angles, right? Also, look what I tried to do. AH, right? What does AH represent for both triangles? What do they represent? Hypotenuse, right? So you guys remember the HL theorem, hypotenuse leg theorem, made from a few months ago, right? The proofs on the walls there. These two terms are congruent because they have the same hypotenuse. They have legs that are congruent, and they're both right triangles. So if these two are congruent by HL, then I can say JH equals FH. Do you remember that theorem? Was that what that reason's called? When after you prove the triangles are congruent and you try to prove other things are congruent? Remember that's called? It's like it's 5 letters. CPCTC, yeah. So by CPCTC, that's why this is true. That's why we always learn triangle congruence early on. We build on that knowledge. So that's tangent segment theorem. Again, I don't expect you guys to know all this today, but I just want to at least introduce it all. Let's keep moving. Here. Can you read first? That's the triangle. Then you can go. Yeah. Central angle.
That's the center of the circle. Part of the circumference edge of the circle, the measure of an arc is equal to the measure of the pencil angle formed by its center. AB is an arc, angle AOB is pencil angle, and angle AOB is equal to circumference AB.
Yeah, good. And you can go. Yeah, so we've talked about arcs already. That's going to be new, arc length. And we know how to calculate it because we do like this angle divided by 360 times the circumference, right? But more specifically, the measure of this arc is the same measure of the same. They're equivalent. As it makes sense, right? Like that's 40 degrees, that's 40 degrees, right? So that's like, let's say if that's 45, that's 1/8 of the whole circle. That's 45, that's 1/8 of the whole circle. So they're always equivalent, just so you know. And then Reagan, can you read the part about versus minor arc, major arc?
Less than 180. Major arc measure is greater than 180. Semicircle arc is measure equals 100. To indicate the major arc of semicircle arc, add an extra point and use 3 letters. And there are 2 measures of it. 1 is the length of the arc, 2 the degree of the angle.
Yep, thank you. Perfect. So I think that's pretty intuitive. Major is bigger, minor is smaller. By the way, the red and the green arcs, what do all these add up to, both these arcs? 360, yeah. So 360 minus major gets you minor, 360 minus minor gets you major. If it's half a circle, called semicircle, it's 180. And right, you care about the length and you care about the degree. Those are the 2 things you care about. So, okay, so we have that terminology down. I think there's a couple more down here. Colette, can you read the part about arcs and chords? Yeah, so if I draw 2 chords, whatever arc it intercepts means it forms. Naturally, that seems to make sense. And again, you could actually try proving it, and we'll get to there when we actually have these discussions, but if I were to draw this and draw this, what's true about both these triangles? They're equal, the same, right? Yeah. So wouldn't that mean that these angles are also the same? So it means that these arcs are also the same. So they all kind of follow a nice logical flow. This is the beauty about geometry. It's very logical. Everything comes so logical at this point. Colette, can you read the bottom? Sorry, Faith, bottom right. Yeah, and all those things are true. So bisect means cut in half. We know this. Perpendicular means it's perpendicular. And you're cutting a chord in half. So the chord, I'll highlight in pink. The chord's right here. That's a chord, right? The permanent bisector will go light blue. Is right here. So it's the whole diameter, I suppose. Yeah, what's going to happen is that you're forming these right triangles again. They're congruent. So great. So that's what's happening, right? So I have PMM and PNL. Those are the same triangles, right? Because you have right triangles, you have the radii, you have the same leg. So naturally, MN equals LN. And because these angles are the same, the chords are also the same too. So that's happening. I don't know if we should really talk about the second page. Yeah, let's hold off on that. Now it's getting a little too complicated. We can come back to this later. But there's a lot of theorems, as you can tell. This is actually going to be your saving grace, this stuff here. I had this crazy idea early this morning that I don't want to provide any formulas or calculus for this next test, but I think it's really cruel. Well, the reason why I bring this up is that I'm not too happy with my E period, and I want to force him to learn this stuff instead of memorizing. But it's not fair to you guys. And actually, look at this, it does look kind of scary. So I might change my mind. I think it was just impulsive this morning, but I'll give all these. It's a lot. Anyhow, they just bombed the test. Yeah, like half the class failed. But they're also not doing their homework either. So I have to have a heart-to-heart talk from today. So come to Jesus moment. Yeah. Yeah, talk to your brother. Actually, that's a solid right there. Anyhow, yeah, so yeah, it's very form intensive as you can see. I'm not gonna talk about this right now because it's too much. And honestly, I think I'll give you these. I think I'm just being kind of crazy saying I wouldn't give them to you. And calculators, yes, I'll give you calculators, it's fine. But I think what we do want to do is we want to understand why these work the way they do. I think that would be good. We should have a discussion about why they work. But these are pretty intense formulas. And to be honest, some of these formulas, if you don't use them, like you forget them after a while. Like these are very obscure formulas. And actually, some of these are not even covered in SAT because they're just so obscure. Yeah, they're very, yeah, they can be. Okay, anyhow. So now let's move on to our topic for today. We're gonna do 9.1. That's gonna cover pages 2, 3, 4, and actually, we'll see what the plan is for today. Give me a sec. I'm supposed to do more than 9.1 today. I think our plan for today, yeah, I don't know if we have to necessarily do all of 9.2, but we'll see how far we can get, and then I'll have you guys work on homework. And actually, I don't think I'm gonna do a Desmos with you guys. I think I'll have you guys do the textbook stuff. I'm gonna punt on the Desmos. So okay, but I'll tote the homework as when I'm done. All right. Anyhow, let's move on to let's see how far we can get today. All right. So basic terms. Again, we know this already. Circles have all points in a plane at a given distance from a given point in the plane. The given point is the center. The given distance is the radius. The chord we talked about. The secant we talked about. Diameter. So if I just do quick diagrams again of what we already discussed. Switch back to this here. So circle, circle, circle. Do my best job drawing a circle. So that's a chord. That's a secant. That's a diameter. And of course, that's a tangent. Ah. So be familiar and comfortable with these terms. So chord, segment that touches 2 points in a circle. The secant cuts or passes through it. It's just a line. Diameter is a chord, but happens to include the center. A tangent just touches at one point, and the point that we touch we call the point of tangency. Okay, so that's the terminology there. A sphere, you guys already know what a sphere is. It's a set of all points of equal distance from a fixed point. However, it's three-dimensional. So a sphere essentially is just oh, do you need to go back? You guys need to... There you go. No worries. There we go. It's correct. It's a chord, but you extend it. Right. It's a little bit more than a chord. And a diameter, as you know, just crosses the center of the circle, and a tangent is just touches the one point. So, okay. A sphere is like a 3D circle. If you took a circle and like rotate it in so many different ways, you wind up sweeping or forming a sphere, right? So that's all it really is. Congruent circles have the same radii. Concentric, they share the same center, but probably will have different radii. A polygon, inscribed in a circle. Inscribed means inside. Circumscribed means outside. And both these things mean that each vertex of the polygon lie on the circle. Okay. Oh, so the circle's outside, right? Fine, whatever. Now, can you draw a circle inscribed in a polygon? Sure. You could do this. Okay, that's a crappy looking circle, but just go with it. It's not good looking, but so the answer is yes, you can. And by the way, these are tangent lines, just so you know. By the way, what do each of these angles add up to? Yeah. And it's not a coincidence. I mean, they could all be different lengths, right? Or sorry, different measures. But it's not a coincidence that's the same degree of a circle. We'll talk about that later. But it's not a coincidence. You'll see why when we get to these theorems later in the unit. Okay, let's do some naming of stuff. And then we'll do some math with this stuff. Actually, why don't you guys name it? You guys figure it out. I will check in with you in 2 minutes. Go and do 1, 2, 3, 4, 5, 6. No, they're not. Nope. Nope. Okay. Yeah, so SI as a segment is a chord, but as a line it's secant, right? And then diameter IN, tangent, even if it's a segment, you still call it tangent. Point I is point tangency, OI is a radius. Okay. So we're okay with that? Okay, now we're gonna do some math. I'm gonna have you guys work it out. Maybe you guys can handle this. So given what you see, work this out. Tell me what you get. And also for the one in the lower right corner, draw a circle O with radius 6. Then draw a radius OA and OB to form an angle 120. Find the length of AB. I'll have you try to do that as well. So you can see this is very computation heavy again. A lot of computations going on here. So I'll do this on my own and we'll check in about a couple minutes. Yeah, what's up? Of course, yeah. All right, how are we doing? You guys still working on it? Yeah, just the 4 problems in the boxes. Work through them. Ask questions. Yeah, good, yeah. Okay, hopefully the top left was fine, that's 5. You use 45, 45, 90 ratios. You kind of see up the top right corner. So 10's hypotenuse, x would be 5√2. Or you could do Pythagorean theorem, x squared plus x squared equals 10 squared, and solve it. For lower left corner, you have 4 and 4, plus 4√2. Again, you can do Pythagorean theorem if you want to. And for the lower right corner, raise to 6. OA, OB, obviously your radii. Then 120. So actually, did I make a mistake with that one? Guys, I messed up. I messed up, guys. I messed up. I just realized it. Here. How about this? Does that work? Because it's 120, right? The angle between the two radii. So that should be 120. But here's how I messed up. When I split it, I thought it was like 45, 45, 90. That was dumb. When I split it, it should have been. Okay, that was not. I was careless. Thank you. I appreciate that. That's 60 degrees. So yeah, so that's 60. Yeah, so sorry about that. So if that's 60, then that means this is 6, this is 3, and that's 3√3. So therefore, this right here is 3 root. Which part? Oh, I mean this? No, that would say arc AB. It would have said arc, or would have actually they should have had this little symbol here. But anyway, so the answer is 6√3. Because what's happening is that you have a 30-60-90 triangle where the dotted or dashed, the dashed or dotted blue line is 3. That's opposite, because this is 30 degrees right here. So that's 3. And of course you have 6 as hypotenuse, so you have 3√3 for the other leg. But since you have to do it twice, we'll say it calls like D, for example. DB is 3√3, AD is also 3√3, so AB is 6√3, right? So yeah, you can see how we start getting a little more intricate with the 36-90 stuff and the 45-45-90 stuff. So yeah, so yeah, my apologies. It was 6√3. My previous answer was incorrect. Okay, we're good. All right, let's keep moving. All right, draw 2 congruent circles, radii 10. We'll talk about tangents after that. All right, so congruent circles. Hold on. Each passing through the center of the circle. Wait, what? Hold on. With grades, each passing. Oh, the center of the other. Oh, got it. Okay. That's confusing. Yeah, go ahead. Yeah, it's kind of like the Olympic rings, the emblem. I'm really struggling here to draw this. Okay, well, that's the best I'm going to do right now. So let's say finally to the common chord. Oh. Okay, that's kind of crazy. That's common chord. Okay, so the black segment, let me highlight it. Okay, that's common chord. So each have radii 10. They pass to the center of the other. Okay, so the purple circle pass through the red center. The red circle passes through the purple center, right? That's what we have here. Okay. How do I do it? How do I figure out the length of that black line? What do you guys think? It's a little nuts. I like that idea. That's a fantastic idea. Yeah, I totally agree. Correct, because the dashed pink line connecting the two centers has to also be 6. That also, sorry, 10. That's also be 10. So 10, 10, 10, 10, 10, 10, right? So, but we imagine that this black line is cutting the dashed pink line in half. So it's 5 and 10. So 5 is your leg, 10 is your hypotenuse. So what is that going to be? We'll call it X. Or maybe you recognize this is a 3690 ratio again. Because the leg is half the hypotenuse. Do you see how it's 5 root 3? We got to double it up. So you get 10 root 3. We're good? Cool. All right. So that's 10 root 3. Yeah, a little tricky, that one. So, but I like Faith's idea of drawing a triangle. It made sense. That was you, Faith, right? Said that? Yeah. So tangents. What's going on here? So if a line is tangent to a circle, then a line is perpendicular to the radius. Okay, we talked about this already. If a line in the plane of a circle is perpendicular to a radius, that's our point. It's a tangent line. Okay. So yeah, so that's what's happening there. So we have this. Sure, yeah. So corollary is basically kind of an extension to a theorem. Corollary, yeah. And that's kind of a funny word. I don't want to do any proofs, like formal proofs, but I think we just talked it out. Like PA and PB are tangents, so we know PA is perpendicular to AC. PB is perpendicular to BC. So you have two right triangles. We also know that AC is congruent to BC. And know PC is a shared hypotenuse. So we have enough. Triangle, because of all these reasons, right? Then triangle PAC is going to triangle PBC by HL theorem. And therefore, PA is congruent to PB. I know I didn't do this in a very linear fashion, which I kind of go against my own words because I sometimes get upset when people don't do that. So here's like the actual steps. So the tangents, you can state that these are perpendicular, you set it so here. And then you have two right triangles, the AC, BC are the same, for both radii, PC is shared hypotenuse and reflexive. So this is true. It's hypotenuse theorem in the course. P equals PV, and that's like a CPCTC situation. We already talked this out about half hour ago. So I won't ask you any proofs, don't worry. But we just want to understand why it works. So you don't want to just memorize it. Let's understand it. It makes sense. We've learned this already. We know why hypotenuse theorem works. We've seen it already. And that's what's happening here. Flip. May 14th for you guys. Mother's Day? No, that's a Sunday. It's a Thursday after Mother's Day. All right. So some prox problems should be pretty straightforward. So AR is 6, RT is 8. Solve for AT. Here ATR is 45 degrees. RT is 4. Solve for 18. So this should only take about a minute, maybe less. Let's work that out. Would you agree? 10 and 4/2? Yep. Okay, easy. Okay, in the diagram below, let me have you try the first two diagrams. See how that works for you guys. Actually, let's do one at a time because it might be a little too much. So I do want to finish off this page so we have a sense of completion. So work on the first diagram. There's 6 things to find. Label, figure it out. I'll help you guys if you guys get stuck, right? I'll help if you get stuck. I hope, yeah, actually, I do hope you guys get stuck. So I can help you. It's that purpose in my life. How are you doing, Mom? Yeah. Oh, cool. Yeah, either I'm gonna watch it Thursday or Friday. Thursday, doing a teacher preview. I feel this first one's a pretty good test question. This first one's a pretty good test question. It really forces you to kind of use all these skills.
How would we know if it's a right angle?
The tangent. You told us the tangent. Okay, you guys get that? 4, 15, 8. So NR is a hypotenuse, right? We're cool with that? How do you do it? Tell us. That works too. That same thing. It's the same thing. Yep. But it's a kite with 2 right angles. Be careful. Don't spill your coffee or water. Okay. Yeah, then MQ is 5 because you have P. Here's the thing. If the diameter is 16, the radius is clearly 8. And that's a circle that the diameter of this small circle happens to raise the big circle, right? That's the way it's set up. So if this is 8 here, then NP is 4. And of course, pull that 3, so that's 5 in the Pythagorean term. Of course, that's 15, that's 15. So yeah, one's kind of one domino falls, all the other dominoes fall, right? They all just kind of all crumble. So okay, let's try the second diagram. So JK is tangent to PQ. Okay. So it means that this is a right angle. And that's also a right angle. Tangent. Because it's tangent, that's why. That's how you can tell. So I know this is 11, by the way.
Oh, so whatever.
Correct. 100%. Yep. I know that's 3. Let me think here. I am so off today. Hold on. What is wrong with me? How come I can't do this? It's probably because it's slanted. Okay. My OCD and perfectionism is coming into play now right now. Here. Do this. Make it worse. There we go. Forget about dashing it. Okay.
Oh, the 3 and 5.
We're on the other side. Yeah, that's clear 17. This is why it's very cryptic, right? It's like a puzzle. That's 3. Therefore, that's 3. How do I know that? Because what I was trying to draw, and a few times I kept going visually, but I figured you gotta let me pass on to a small line. This pink line here, would you agree it's perpendicular to JK? Yeah, because it's perpendicular, these have to be 3 each. That's 3, and that's 3. Therefore, this remaining portion is 8. And that, so I do Pythagorean theorem to get the pink line. If the pink line is 15, then what's JK going to be? 15. There you go. And that's how you figure it out. I've actually seen like standardized testing questions, like SAT questions that have that. And these are sort of like the hard questions. But that's also because people just forget this stuff over the years because they don't really reinforce it. But it's also a little hard to see too. So by taking the triangle, putting it elsewhere, and then kind of focusing on that, so I figure, oh yeah, 8, 15, 17, I got it, right? So we're good. Okay, last one, just to get a sense of closure. And we'll actually be ahead of. Hmm? Good. Yeah, exactly. Correct. Yeah. We 17. Because remember, it has to, form a triangle. Okay, last one, just to get a sense of closure here. And also we have Mr. Davis's class. That's good. QT is 6. PR is 30. TR is 8. Therefore, that's 10. Right? Because that's Pythagorean theorem. That's a right angle again. Okay. I know that kind of fast. I only got 70 seconds left. Okay. So hopefully you guys see how QR is 10. If QT is 6 and TR is 8. 6, 8, 10, we know that as a ratio. Since we know PR is 30, then you have no choice to make QT 20. Now these are some triangles, by the way. You have 2 right triangles. These right are parallel. So what's the ratio between QR and PR? It's 1 to what? 1 to 3. Therefore, this is also 1 to 3. That's why it's 18. And then I need RT to be 1 to 3 RS. If that's 8, then this is 24. Therefore, SC has to be 16. We'll talk more about it. So, homework will be textbook stuff. Look at Schoology. Just go to CPM textbook. I'll make a copy and scan it during my free period. Sorry to make a photocopy. Oh, test. I need a test back. Double talking about the money deal with other. Here. Sure, yeah, go over. Yeah, he's great. Yeah. Oh, come on. Well, I might be willing to kind of, say, let's roll this. You know, like, repeatedly. Hold on. Well, you lost half. Geez, yeah, I think I have 2 points. I might be willing to give a point back. We can talk, just come by, I might be willing to give a point back. Yeah. Yeah. Yeah, did you email about that already? Maybe someone else did. Okay, yeah, that's fine. No problem, yeah, no worries. It's all good. See you later. Okay, stop that.